So I've been playing around with the circuit a little bit more, and I made an attempt to increase the headroom, which seems to work really well. But what I've done is I've adjusted our power supply to provide 550 volts to the top here, which supplies our 6AH4 and our cathode follower. I haven't changed the resistor between this supply node and our 400 volt supply node for our 6SN7, so this is now at approximately 450 volts, which is fine. But this has really made big improvements on our headroom, while also, or taking into account adjusting our 6AH4 operating point and putting a little bit more current through it. So the bias, instead of 25 volts, is now static 27 volts. So that gives us 2 more volts of input headroom on the 6AH4 compared to before, which keeps us away from the grid current region and gives us a little bit more margin for grid current. But it also centers this up better for our 500 volt supply and gives us more headroom. So with that, we can now tolerate a bit more signal. So here's 1 volt, or 1 volt input. You can see it's very clean now with 0 signs of clipping. And now I can go all the way to 1.1. And we're just starting to maybe see a little bit of clipping there on the top. It's just starting to roll over. That gives us an output of 12.58, 12.59 volts. If we do the math, 12.59 times our gain factor for our voltage divider loaded by our AP, 204 volts peak, so that's about 208 volts peak to peak. That's really good, and we got our headroom back, and we've got a lot of margin compared to where we're nominally going to operate this, which should give us plenty of headroom on this driver, and we should be able to meet our peak output power by driving our 845 grids really healthily with strong voltage and strong current drive. And in fact, actually, based on the load line analysis with a 550 volt supply and where our critical load line, where our load line rotation becomes critical, as I've shown before on those curves based on the load impedance, this parallel cathode follower with 30 milliamps with the constant current source can drive nearly 2.5 watts RMS output power. So this is a really robust driver, and I'm really happy with it. And like I said, the performance, it doesn't really matter where I connect my AP, the performance is still awesome. So what I wanted to show before I close the video out, not only is the headroom change, but I wanted to show a little bit better view on the grid current issue. So like I said, now it's much less of an issue because we've pushed the headroom and we've got a lot more headroom. So the likelihood of us running into this as a real problem in the real world is going to be very minimal. But if I go back to burst mode, what I've done is I've connected a different oscilloscope. So I've got this computer running on top now. This is called a picoscope, which is a little USB oscilloscope with 2 channels. It's really nice. So right now I'm just monitoring the output of our 6BX7 across our voltage divider. And what I've been doing is I can run some burst testing with some longer time scales, because this captures much better than, this old analog scope at really, low time scales or long time scales. It's really hard to see on the camera, and so I figured I'd show it here. So this is what the burst looks like with 10 cycles of high amplitude to 50 cycles in total, so 40 cycles of low amplitude. So that's how I have the AP set up. 10 cycles of high amplitude, 50 cycles in total per interval, which means 40 cycles of low amplitude. I'm at our 1.1 volts, and you see what that looks like. It looks really nice. What I'm going to do now is punch up the input voltage to 1.5 volts. You can instantly see what's going on now. At these higher signal amplitudes, we can see the bias drift back towards center bias before our next burst comes. So the amount of bias pumping or offset of our bias point versus time is a function of the time length of our high amplitude burst that causes grid current, as well as the amount of time it can relax before it sees another burst. So for example, if I just do one cycle of high amplitude signal at the same conditions, notice how we have very little bias shift. We're not accumulating our shifting bias due to the asymmetric time constant created by the grid current. One cycle is not enough to accumulate enough charge across this capacitor to shift the bias appropriately. But if I move to 2 cycles, 3 cycles, 4 cycles, and so forth, all the way to here's 10, the problem gets a lot worse. If I push the amplitude higher, there we go, we're back. If I push the amplitude of our peak signals higher, the problem gets worse as well because we just draw more grid current during this burst duration. So instead of 1.5 volts for our input signal for the burst, I'll do 1.7. You can see what happens. At some point, if we drive and shift our bias hard enough, this region will also be pushed towards cutoff. And this is what I was getting at when I was talking about blocking distortion. This lower amplitude signal can actually be blocked by the shift or offset of the bias during a larger amplitude swing. And so what we would ideally want is this recovery time to be extremely quick. That way, yes, we may have a little bit of distortion for peak transient, but it'll pass extremely quickly with, due to the peaky and dynamic nature of music. You can pass that region very quickly as long as, right after we can play audio. With blocking distortion, if this isn't managed well, you'll have a region much beyond the audio transient itself that won't be represented accurately, will be highly distorted. So maybe we can push it there if I increase, maybe let's go to like 2 volt input signal. There you go, you can start to see. We're starting to flat top even this smaller amplitude signal. And notice how we're really still a long way away from letting it recover all the way. So if I increase my interval number of cycles to 75, we're still decaying. So it takes a long time for that RC time constant to normalize again. Looking back at the schematic here, one thing I realized is when we tested this 6SN7 mu follower, the 6SN7, the top tube, is a cathode follower output. We're driving 470 k ohms. If we reduce this resistance, we can speed up this time constant while still having good low frequency performance with this coupling capacitor, and that will dramatically increase our recovery time after a burst like this. And in fact, we know we can get away with this because when we measured this, the audio precision we had in parallel with this 470 k ohm, that created an equivalent resistance here of about 82 kilo ohms. So 100K in parallel with 470 is about 82 kilo ohms. So the performance when we benchmarked the stage, we were driving an 82 kilo ohm load. Therefore, this 470 is much higher than it really needs to be. So that's one thing I'll play with off camera, is adjusting this lower resistance value and speeding up our recovery time constant. Now again, for this application, this isn't a guitar amplifier. We're not going to be distorting this heavily under any normal scenario. I mean, we're nearly 2x our input signal what we would have for max power. But should we have a transient that causes some clipping, it'd be really nice if this amplifier recovered quickly anyway. And so that's what we can tailor with that resistor. So I think now I'm done with the documenting on how this stage is performing, at least on the bench. I'll end up running a lot more tests of bandwidth, THD versus output power, THD versus frequency, and changing in different tubes to assess the performance across tube variation. I'll roll all that up and then do a separate video on that, probably in front of the computer, showing all the Excel data and how this finally wraps up. But I will say with this 550 now volt supply, this thing performs awesome. I mean, I couldn't ask for anything more. This is going to provide all the signal swing and then some we need for our 845s, and plenty of current to overcome the slew rate, and also potentially drive some grid current into our 845s for maybe a little bit more output power, or at least a nice transition into clipping with our 845 grids. So thanks for watching again, and take care.